Here we will look at Eisenstein's criterion, which says the following. You have a prime number p, and you have a polynomial with integer coefficients that satisfy the following conditions. The leading coefficient is not divisible by p, but every other coefficient is divisible by p. So this notation means congruent to 0 mod p, meaning the remainder is 0 after division by p. So the first leading term, not divisible by p, every other coefficient is divisible by p, and furthermore, I'm going to say that the last coefficient is not divisible by p squared. So if your polynomial satisfies this condition, it turns out that it's irreducible over the rationals, which, as we know, it's enough to prove irreducible over the integers. So here's the proof. Let's suppose it is. This will be a proof by contradiction. So let's say that I can factor f over the integers. So I could factor it as, I don't know, bk, x to the k, plus a bunch of terms, plus b0. That's polynomial 1, times polynomial 2, cm, x to the m, plus more terms. In the middle here, I'm going to get cj, x to the j, and then this goes down till I get to the constant term c0. These two are polynomials in zx, so integer coefficients. Well, it follows immediately that b0 times c0, the constant term, has to be the constant term of my polynomial. So then b0 times c0 is a0. This means since a0 is not divisible by p squared, one of these two terms is divisible, it cannot be divisible by p. So thus one of either b0 or c0 is not divisible by p, because if both were divisible by p, then a0 would be divisible by p squared. So let's say p does not divide b0. So I'm going to let cj be the first coefficient in this second polynomial that is not divisible by p. I know that one of these coefficients is not divisible by p because if I multiply the two leading terms together, the leading terms, then I get bk times cm. That would give me an in my polynomial, and my leading term is not divisible by p, meaning that the two products of bk and cm are not divisible by p either. So there's got to be a first time that one of these coefficients, reading right to left, is not divisible by p. Let's call that cj. Let's call that cj. Well, then what happens is the ajth coefficient, that's the coefficient in front of x to the j power. That is a product of the b and the c terms. What is it exactly? How can I multiply something in this first parentheses with something in the second parentheses to get a to the jth power? Well, I could start with cj x to the j times b0. So I'm going to write that down, cj b0. If I multiply these two terms, I get an x to the j. I could also get an x to the j power by multiplying the x to the first term here, that would be b1 x to the first, times the j minus 1 power. So I'll get b1 times cj minus 1. I could also get an x to the j power by multiplying the squared term in this parentheses with the j minus 2 term here. And I can keep getting terms until I finally end with the jth term in the first parentheses times the the constant term in the second. Okay, so I wrote the a jth term, that coefficient in my original polynomial, as sums and products of the CJs and BJs. Okay, CJ is not divisible by P. B0 is not divisible by P. So this is not divisible by P. However, every term here is divisible by P. This is divisible by P. Why is that? Every Cj minus 1, Cj minus 2, down to C0 is divisible by P because of the minimality of J. Furthermore, Aj is divisible by P. That's our contradiction. Our contradiction is this whole expression has to be divisible by P. It's Aj, but it can't be because this term is divisible by P, but this term is not. So that's the contradiction. Aj cannot be divisible by P after all because of how we set things up. So that's a proof of Eisenstein's criterion. Let's do an example of this theorem. So let's see here. What if I did 3x to the 5th plus 15x to the 4th minus 30x squared plus 10x plus 55? I claim that this is irreducible over the rationals. Using Eisenstein's criterion, I could pick my prime P to be whatever I'd like. So I'm going to take P equals 5. Then this polynomial satisfies the desired property. The first leading coefficient is not divisible by 5, but all the other coefficients are divisible by 5. And furthermore, this final coefficient is not divisible by 25. So I think that's it. I'm done. I proved kind of a amazing result that this polynomial cannot be factored over the rational numbers. All right,